ladies and gentlemen, welcome to my lecture series Modern Gravitational Theory. This is lecture 6, the Einsteinian field equations. This is a very important point in this series. From now on, we will apply tensor calculus and Riemannian geometry to gravitation. And we will revise the whole general theory of relativity completely. The whole theory does not work because there is no usable metric. Already the inner and outer Schwarzschild metric yields singularities. Singularities are unphysical, and so it's nonsense. It was Einstein's idea to apply mathematics of curved spaces to gravitation. Okay, we want to have a profound elucidation of that procedure. Today we must say to describe gravitation by Riemannian spaces is obviously correct according to our present scientific knowledge, but the mathematical execution was or is still wrong, because the metrics contain singularities. Singularities are unphysical. And here, that is what many physicists haven't understood. They use the metrics to make nice physics. The result is some strange things like event horizons, white holes, and so on. Things which possibly do not exist, instead of making usable mathematics in gravitational theory. And it is possible that the whole concept of Riemannian spaces does actually not work for the gravitational interaction because of quantum field theory. At the moment, we haven't got a working gauge theory for gravitation. One reason the theories are not renormalizable, and the macroscopic treatment of gravitation does not fit together with the microscopic quantum mechanical treatment of gravitation. So perhaps it could be that the whole concept of curved spaces must given up if we have perhaps a working gauge theory for gravitation. Now we come to the Einsteinian field equations. Many people, especially non-physicists, think that it was a great achievement of Einstein to derive the field equations out of first principles. Now, that is not the case. It was a long procedure of trial and error. Einstein made several ansatses for field equations for the gravitational interaction. Once the theoretical physicist said to him, "Oh no, that cannot be." And then on the other side, the astronomers, they told him, "No, we observe other things in space that cannot be." And so he tried one version after the other one. Then he had written down a version that couldn't be disproved immediately at that time. Perhaps if the history of physical progress had made another development, perhaps the field equations would have been dismissed as well. Okay, it was in 1912 as Einstein tried to generalize the Newtonian Poisson equation, in which he substituted the gravitational potential by the velocity of light. So that means, instead of phi, he wrote c. And here another see. But this equation would break the rule of the Newtonian axiom, action is equal a reaction. That means the momentum conservation law then. Einstein was not familiar with tensor calculus, and so he was working together with a mathematician, Marcel Grossmann. He comes from Hungary. And then Einstein generalized the four-dimensional line element. That was what we usually use today here, 217 d squared is the metric tensor g mu nu, and the two differentials of the space-time coordinates. He supposed at that time that a metric for gravitation cannot be constant. Okay. Then Einstein used the ansatz for the GOO component in the metric tensor is c squared, and c is dependent on the coordinates, and that means the velocity of light changes in space. It's not constant. In 1913, Einstein and Grossmann published a work, and there we find the following equation: g mu nu is equal to constant kappa, and the energy momentum tensor T mu nu, 219 here. That is what we use or define today, and the question at that time was then, how does the G tensor, the so-called Einstein tensor, looks like? On one side here we have the energy momentum tensor. That means here we have the masses which curve the space, so they cause a gravitational field. And on the other side, G represents the geometry, how the space is curved. And now mathematical expression is necessary for the G tensor. We have here the principle that gravitation is equal to the curvature of space. It was Grossmann that meant that the Ricci tensor could be written for G, but the Ricci tensor does not obey some conditions which must be fulfilled unconditionally. And because we have in G the geometry, the curvature of space, so the assumption must be made that the tensor, the metric tensor G mu nu, must obviously appear in G. Einstein, he still tried to generalize the Poisson equation and made laborious calculations. And he noticed the following form, 220 here, this one. O stands for higher terms, which can be neglected if we consider weak gravitational fields. That is the same what we often make today if we calculate something for our environment here. We have here only a weak gravitational field on Earth, and there aren't very strong gravitational fields in our environment in space. And so higher terms can be neglected mathematically. If he uses this version, then the Newtonian limit case can be obtained. If Grossmann used the Ricci tensor for G, then the Newtonian limit cannot be reproduced. Einstein was trying out many things to obtain a usable term for the G-tensor. He was using all the things which are available, rigid tensor, metric tensor, the Christoffel symbols, the curvature scalar, and so on. Trial and error. And then he made an ansatz with an unknown tensor tau mu and wrote down for the curvature scalar R, the scalar product G metric tensor with the tensor tau. But here Einstein thought it was too complicated to determine the unknown tensor tau mu. And then he tried another ansatz. Now he wrote down a product with the Christoffel symbol. G metric tensor multiplied by Christoffel symbol. That would have led to the equation 220 that was here with the O higher terms. Okay, it does not work. And the next try was a product of two Christoffel symbols. But here we would not obtain the Minkowskian limit case if we are far away from the mass which causes the gravitational field. Then we must have an uncurved space, we must have the Minkowskian limit case, and that wouldn't be yielded by this expression. Then another try was to split the rigid tensor into two parts, and then Einstein and Huppmann, they didn't make any progress, and so they already wanted to give up the principle of general covariance. Oh my dear. Okay, they weren't familiar with variational calculations, and though they acquired those methods at that time, Einstein made some linear transformations which led to equations with a metric and the energy momentum tensor, and those equations were obeyed by adjusted coordinate systems. They introduced some strange things to obtain usable equations. He noticed that the energy momentum tensor does not change only under linear transformations, else the energy and momentum conservation law would be violated. That is a catastrophe. Until now, we think that the conservation laws of energy momentum are correct everywhere in nature. In 1914, Einstein then recognized that those mathematical developments did not go together, as he moved from Zurich to Berlin, and there he worked together with the astronomer Erwin Freundlich. And they had the problems that there is no correct calculation of the periodic movement of especially Mercury. Rotation seemed to be inadmissible as coordinate transformations, and considerations of the action integral did not yield the requested results. So another point then was to postulate that the square root of the negative determinant of the metric tensor should be constant. And he made a whole series of strange assumptions, ansatz calculations, but nothing worked really. And then on November the 25th in 1914, he then could present field equations that couldn't be disproved immediately by the theoretical physicists or the astronomers and so on. He found out that the energy-momentum tensor cannot be traceless, as he was considering the gravitational field of the Sun, and so he found a version which reproduced the Newtonian limit case correctly. And so we have for vacuum here this equation 223, and in general here we have then the energy momentum tensor capital T here in the equation, this one. And this can be transformed into the equations we usually use today as the Einsteinian field equations. Usually we find this version, but another equivalent version, this one here, can also be used, means the same. Now these two representations are equivalent. Let us see how. We multiply here by the contravariant metric tensor G mu nu. So that means that we have R mu nu covariant and G mu nu contravariant. That is the curvature scalar R. Then here we have G mu nu co and contravariant. That means we get Kronecker delta. And on the other side we have an additional G mu nu tensor to the energy momentum tensor. And then if we use that the curvature scalar is equal to the constant kappa and the inner scalar product of the metric tensor, then we can write for R kappa T, and then we would get here these second version here with two T's. Okay. We want to emphasize here that Einstein had not found the equations by a consequent derivation out of first principles. No. He had fiddled around as long as he had field equations which obviously satisfied all the requirements. And now the Einstein tensor, like we use it today, is R mu nu minus a half metric tensor G mu nu multiplied by the curvature scalar. This is the only one form that includes the metric tensor G mu nu and its first and second derivative over the Ricci tensor. And it is divergence free, the G mu nu tensor then. Then, by using the theory, the field equations, some defects of that general theory of relativity appeared. For example, here are some of the most important ones. The field equations allow too many solutions mathematically, and so we have solutions which are mathematically correct, but they are unphysical. The field equations are too general. Then the matrix which we have in GTR contain singularities. Singularities are also unphysical. And that was recognized by Hilbert already in 1917, that there is no conservation law for energy and momentum. My God. Then the formula for gravitational waves, which was given by Einstein, was not derived from the theory. And the geometrization principle in GTR is obviously wrong. We will consider all that during this lecture series. Then it was Fock in 1959 who derived another solution. He has used another coordinate condition, that the one that is used in the Schwarzschild solution. With this additional condition, the number of possible solutions was reduced, and that condition for the Fock metric makes more sense if we look at quantum field theory for gravitation. But the problem was then nobody has taken notice of the Fock solution. Later, other Russian physicists were using the Fock metric to work out other things, especially the relativistic theory of gravitation. Deriving some generally valid solutions for the field equations is relatively complicated. So here we have a list of metrics which were derived. In 1916, that was shortly after Einstein had published his field equations, Carl Schwarzschild derived a static spherically symmetric solution. First an outer one for vacuum and then the inner one for a mass-filled space, for a sphere with a constant mass density. The problem here is it is not usable. It contains singularities. If a theory contains singularities, the theory is wrong, must be wrong. Here, instead of make a better theory, the scientists rather make science fiction and postulate such things like an event horizon around black holes. Probably there is no event horizon. A black hole is a body with a still higher mass density than a neutron star. And of course, if an object is nearing the black hole and it comes too close, then it cannot escape anymore. And so it crashed onto the body, onto the black hole. But probably there is no mysterious event horizon. We will work out everything here in this lecture series in detail. Then we have in 1918 the H. Reisner G. Nordström metric. The Reisner-Nordström metric is an extension of the Schwarzschild solution to electrical charges. That means, we have a body which has an electrical charge, although spherically symmetric, static solution. Here the same problem. It's an extension of the Schwarzschild metric, so it contains the same singularities, so it's not usable. Here in this list we can say the level of difficulty to derive a metric mathematically is increasing. In the Schwarzschild metric, an additional coordinate condition was used with the aim to simplify the system of differential equations. In deriving the Schwarzschild metric, then we have only two unknown functions instead of three. Originally we have three unknown functions here. And so deriving the Schwarzschild metric is relatively easy compared with other matrix here. Then in 1937, H.P. Robertson and A.G. Walker, they introduced a time-dependent spherically symmetric metric, the so-called Robertson-Walker metric. With that metric, we can describe the development of the universe. But here again, it has singularity, and this metric is obviously too simple to describe the behavior of the universe correctly. Yeah, if we work here with that metric, then there is one reason why such strange things like dark energy was introduced. Because the metric does not work really, and so instead of work out a better mathematical description, some strange things like dark energy were postulated. Oh my god. Possibly there is no dark matter. That reminds me on the situation around 1900. Everybody was searching for the so-called ether. And then it turns out, oh, there is no ether. Electromagnetic waves don't need a medium. And perhaps here that's the same situation. Everybody is searching for the dark energy, dark matter, and there is no dark energy or dark matter, possibly. Then, we can say that the next degree of difficulty, mathematically, in 1959, V.A. Fock derived a static spherically symmetric outer solution for the theory which we call today the relativistic theory of gravitation, RTG. The problem is, as Fock derived that in the Western hemisphere, perhaps, they didn't recognize the Fock solution. So it stayed unknown, we can say. Later, as Russian physicists worked out modification for GTR, then they recognized that the Fock metric is the static spherically symmetric outer solution. Then in 1963, R.P. Kerr derived a static axisymmetric outer solution for GTR. But the metric is completely unusable. It contains many singularities and higher terms are neglected. That means the Kerr metric can, if at all, can only use for weak gravitational fields and low angular momentums. And what do the physicists do? They calculate the most adventurous things for black holes. That's nonsense. The Kerr metric is, we can say, completely disproved. It is not possible to construct an inner solution to that. And of course, there is an inner physics. If we have a rotating body, rotating star, neutron star, or whatever we consider. And so an inner solution must exist. So we can forget the Kerr metric. Then in 1965, E.T. Newman, he extended then the Kerr metric for electrically charged bodies. It contains the same singularity, so the Kerr-Newman metric is also not usable. Then in 1985, A.A. Vlasov and A.A. Loganov derived a time-dependent spherically symmetric solution for RTG, for the relativistic theory of gravitation, to describe a development of the universe. Then in 1987, the same physicists, Vlasov and Loganov, derived a static axisymmetric outer solution for RTG. That's the counterpart of the Kerr solution in GTR. Yeah, but that solution is obviously also unusable. It contains singularities. And yeah, okay, the treatment of the metric to calculate anything is very complicated. Okay, at the present state of our knowledge, we must say we haven't got a usable axisymmetric solution in gravitational theory. In 1989, P.V. Carabut and Y.V. Jugrave, they extended the axisymmetric solution to electrically charged bodies. Okay, problem, singularities again. And then we can say here we reach the next degree of difficulty to derive a solution in gravitational theory. H. Huppmann, German physicist, derived a static spherically symmetric inner solution for RTG. Yeah, H. Huppmann tried to publish his work, but now Physical Journal wants to print his works, and so he was forced to publish that work, his metric, in a kind of lecture on YouTube. Here we have all the sources for the metrics, and also we have the source here of YouTube for the lecture for the Huppmann metric. And here, now, that is interesting, the Fock-Huppmann geometry is probably free of singularities. And there are some experimental hints that the Fock metric, the vacuum solution, works better than the outer Schwarzschild solution. And possibly the inner solution, the Huppmann metric, does also work better than the inner Schwarzschild solution. Now we will look at all these metrics in this lecture series. Now we come to the variation principle. Einstein had found the field equations by procedure of trial and error. But this is a very important principle in physics. Field equations, equations of motion, can be derived from a Lagrange density function by applying a variation calculation. And so it must be possible to derive the field equations from a Lagrange density function. It was Hilbert who had found a variation principle which yields the field equations. The question here is, how does a Lagrange density function look like? Okay, a Lagrange function is a scalar. And so we are asking which scalar quantities have we got in gravitational theory. We immediately think of the curvature scalar, R. So we make an ansatz with the curvature scalar for the Lagrange density function. We write here an additional factor, square root minus g. G is the determinant of the metric tensor. If we make the calculations, then later we would see a factor is missing. Okay. Then the term square root minus g d4x is invariant under coordinate transformations. Yeah, exercise for students shows that. So we write for the variation of the action integral here. Yeah, we substitute L here by square root minus g r. and the variation must vanish, must be equal 0, 228 here. We must recognize here that we only consider one gravitational field and no other things. No other bodies, fields or anything. Only a pure gravitational field. So we write now for the curvature scalar here in 229 the scalar product of the metric tensor G mu mu contravariant and the Ricci tensor R mu mu covariant. And then we write the variation in two dents here. In the first we vary the Ricci tensor here, delta R mu mu. And in the second integral we vary the things with the metric tensor, square root minus g, the determinant, and g mu mu. We need the variations of some tensors, and so we consider these variations now. First, we begin with the Riemannian curvature tensor. The definition have we got here, 230. And if we write down the variation of the tensor, then we would have a delta here in the first two terms. The differentiation and the variation are commutable. And then in the third and fourth term, we have got a product of two Christoffel symbols. So that would mean for each term we get two new terms. For the third term here, we have here delta, the first Christoffel symbol, the variation of the first Christoffel symbol, and here of the second Christoffel symbol, and the same for the last term here, two other terms with a variation, 231. Then we consider the covariant derivative of the variation of a Christoffel symbol. That's what we have here in 232. According to the definition of the covariant derivative, we have here four dents. The first one is the partial derivative, and then we have three indices in a Christoffel symbol. That means we have got three additional terms here in the covariant derivative. And now we solve the equation for the partial derivative here. Okay. And now we substitute in 231 here the first two terms, means the partial derivatives here, by 233 here. And then we get a longer equation here, 234. But here we can cancel out some terms, or many terms. For example, the second term here in the first line is identical to the second term in the second line here. But here we have a minus and here we have a plus sign. The only difference is here we have in the internal scalar product the index gamma and here lambda, but that makes no difference. And if we consider the third term here in the first line, then we find it is the same like the third term in the second line here. Again, we have different indices for the scalar product here. And here we have to recognize that the two indices of the Christoffel symbol are commutable. We have a symmetry here. That means gamma beta mu is the same like gamma mu beta here. And so this is the same like this, but here plus, minus, we can cancel that out. And so we can cancel out other terms or all terms but the covariant derivatives. So the result is we have for the variation of the Riemannian curvature tensor the difference of two covariant derivatives, 235. And so we can write the variation of the Ricci tensor. The Ricci tensor is the result of an internal scalar product of the Riemannian curvature tensor with an identical index above and below here, alpha. And so we can apply 235 for these indices. And so we have also the difference of two covariant derivatives. The result that the variation of a tensor is the difference of two covariant derivatives is called Palatini identity. Now we consider integral 229 here again. Here. And now we can substitute the variation of the Ricci tensor here. 237. And here we write the metric tensor G mu nu into the parentheses, both parentheses. This is possible because the covariant derivative of the metric tensor vanishes. It is 0. Okay, let us see why. Now we write an equation here. G mu nu differentiated with respect x alpha minus, here a product of the metric tensor and Christoffel symbol. And here we can write, instead of a Christoffel symbol of the second kind here, we write here a Christoffel symbol of the first kind by using here another metric tensor. This metric tensor G beta gamma, with a gamma here as an upper index and a gamma here as a lower index, means we got a beta as an upper index at the gamma than what we have here. So this is a correct equation 239. Then we work on the right hand side of the equation. We have here a scalar product in the two metric tensors. That means we would get a Kronecker delta gamma mu. And gamma as an upper index. Here we have gamma as a lower index. That means we got here, instead of gamma, index mu. This here, 240. And then we write for the last Christoffel symbol here of the first kind, the definition here, 241. And then we see, here in the parentheses we have the same term, the same metric tensor like here in front of the definition of the Christoffel symbol. So we can add them together. Here we have plus 1 minus a half means plus a half G mu nu alpha. And we multiply the minus into the parentheses. That means this minus gets a plus and this plus term gets a minus here. Here we have the definition of another Christoffel symbol of the first kind. And so we can write here 243. Okay. And now we consider the covariant derivative of the metric tensor G mu nu. Okay, we write it down. Then we have, according to the definition of the covariant derivative, here a partial derivative, and here two terms with the Christoffel symbol. And that shall vanish, we said. And now we can substitute the first term here. We have the same here in this equation 243. That means we have this Christopher symbol, gamma, mu, alpha, mu, plus this product of g mu beta and gamma beta mu alpha. So that's what we have here in 245. We have substituted here this term. And now here we see now the second and third term are identical but with different signs, plus and minus, so this is cancelled out. And then we have here a scalar product, beta as a counting index. That would mean we get a gamma, mu, alpha and mu covariant, and that is the same like the first Christoffel symbol here in the equation. This is plus, this is minus, so we can cancel out them too. And so, yeah, the result is 0, and so we see, yeah, the covariant derivative of the metric tensor vanishes. Then we continue with the integral. This was our integral, and yeah, we had written here the difference of two covariant derivatives. We have changed the index for a scalar product in the second term. Yeah, it makes no difference which index we use for an internal scalar product. So we can factor out the covariant derivative, d alpha, here. And here we have the equation 247. Then we know, we have seen that a Christoffel symbol is not a tensor. But the difference of two Christoffel symbols is a tensor. Yeah, this is an exercise for students, shows that. Very easy. You have to apply the transformations and you see, yeah, it transformed like a tensor. Okay. We have here the difference in the bracket. And yeah, we have a scalar product in two indices, mu alpha here, or here mu. And that means that all indices are vanishing, but alpha. And so we have a contravariant index, alpha, that means, yeah, this is a vector. We call this vector here v alpha. 248 here. And then we write down the covariant derivative of the vector here. Yeah, according to the definition, we have here this means, yeah, the partial derivative plus a term with a Christoffel symbol. And now we use equation 199 here. We had that in an earlier lecture. We had showed that. And so we can substitute for this gamma, because we have an identical index above and below alpha, and so we can write this expression here. Or we can apply the product rule of differentiation, but in the reverse direction, and then we get this expression here, 249. Yeah, we can verify that. Here we have the differentiation. If we differentiate v, then square root minus g would cancel out, and so we have the first term here, only the partial derivative of v. And if we differentiate square root minus g, then we would have this term, because then we have v alpha as a factor here. Okay. And now we substitute 249 here, this in 248 here, and so we have here 250, this expression here. And now we can apply the Gaussian theorem. That means instead of performing an integration over a volume, we can integrate over a surface. And the situation is now the variation of the Christoffel symbols vanishes at the boundaries. And so, the whole integral would vanish here in our formalism. Now we continue with the second integral in 229 here. So that means we have this integral with a variation of square root minus g and metric tensor. These are two factors in the parentheses. So we get, if we execute the variation, two adends. Here in the first we vary the square root, and here in the second we vary the metric tensor, 251. Then in the first integral we have a scalar product r mu nu Ricci tensor and g mu nu metric tensor, here co and contravariant. That means for this we can write the curvature scalar r again here. And now we need the variation of the square root of minus g. Now the term here, delta square root minus g, depends on g, the determinant of the metric tensor. So to vary, we have to differentiate with respect to g, and then we write delta g here. Okay. The differentiation of the square root, that is square root in the denominator, a factor a half, and a minus from the minus here in the inner function of the square root. And then we have the variation of g itself here. And now we have used in a former lection this expression 198, this one here. And to continue now, the determinant g depends on the components of the metric tensor, g mu nu. And so we have to differentiate with respect to g mu nu here, and then write delta g mu nu for the delta g here. And then for the differential quotient here, we can write here instead, determinant g multiplied by g mu nu. This. And so we can write for delta g here, this, and we have substituted this here. Okay. Then we can write instead of contravariant mu nu indices and covariant mu nu indices here, the opposite indices here, covariant now and here contravariant. But then we have to change the sign here. Now let us see why. Okay, we can write g mu nu, co and contravariant. Here, scalar product is Kronecker delta mu nu. Then we differentiate the expression, and that means on the right side, delta mu is a constant, so we get 0. And then if we differentiate here, we get two addends according to the product rule of differentiation. And then we can multiply by the differential dg mu nu. Then we have this. And then we write one of the addends to the other side, but then with minus. And so we have, this here, 256. We see, if we exchange the indices here from covariant to contravariant and vice versa, then we must write a minus. And so we have for 252 now this 257. And so we have for the integrals in 252 here this expression 257. And here we have substituted what we have calculated before. And now we can write everything in one integral. So that means we can factor out square root minus g, delta g mu nu, and d4x. Same factors in the two integrals. And then in the parentheses here we have from the first integral minus a half r and g mu nu. Here's the first addend here. And from the second integral we get Ricci tensor r mu nu here. Okay, and this whole integral shall be 0, must vanish. Delta g mu nu does not vanish, and square root minus g does not vanish. So the term in the parentheses must vanish. So we can write this 259. And here we have the Einsteinian field equations for vacuum, because here the energy momentum tensor is missing. So these are the field equations for vacuum in curved space. A more general representation can be obtained if we consider a second part for other fields in the Lagrange density function. So we then write for the action integral, besides LG, the Lagrange density for the gravitational field, another LF for other fields. LG would be R, that's what we have considered before now. And so we consider the second part here. If we consider the variation of the action here, then we would get this 261 with square root minus g and LF in the integral. If we carry out the variation, then the independent variables we have now are the components of the metric tensor. And that means we have to differentiate with respect to g mu nu and the first derivatives of g mu nu. And so we get here 262. We have two addends. And now we apply again a partial integration to the second integral here. That means we integrate here delta g mu nu derivative, and we differentiate the differential quotient here with the Lagrange function here. That means here the differentiation of this fraction, and here this is integrated this, and An additional term in front of the integral is both terms not differentiated, so delta G mu and the differential quotient here. Yet this first term vanishes because the variation of the start and end point is 0, is vanishing, and so we have only here this 264. The first integral stays here like we had it here in 262. Okay. And now we factor out the delta G mu mu here. And so we have here, great term. Here now we define the energy momentum tensor. We do that in the following way. T mu nu is this big expression here multiplied with 2 divided by square root minus g. That's more or less a definition here. If we substitute that in the action integral, then we have this here 267. We have T mu nu with the factor square root minus g and a half then. And now we can write for 260 everything under one integral like in 258. And so we have a third term now here in the parentheses. And the term in the parentheses must vanish. And so we get the Einstein-Riemannian field equations again here. This time by a variation in principle out of a Lagrange density function. Now we have introduced here a constant kappa. For the factor in front of t we write kappa now. The proportionality factor. This is called the Einsteinian gravitational constant. It contains the Newtonian gravitational constant. We will see later how kappa looks like. Now we will finish lecture 6. Next time we will talk about the theoretization problem and the variation principle in the relativistic theory of gravitation. Thank you for watching. See you next time. Goodbye.